Sounds good. It's doing what it's supposed to. All right, cool. So we'll go ahead and start up mousepad first because we want to look at the C code. So we'll take a look at power_of_2.c. This is just a C program. So in this case, we are dealing with unsigned power_of_2. We'll just call it P2 as the name of the subroutine. Takes in one single parameter, which is unsigned n. And in the subroutine, we are going to say unsigned result so that we don't use a return in the middle of a conditional statement. So unsigned result. And then we say if n equals to 0, then we can stop the recursion because we know exactly what the result is supposed to be. So result is just 1 in this case. Otherwise, we'll say result is 2 times P2 of n minus 1. And then over here, we say return result. So that's a recursive way to compute 2 to the power of n. Are there any questions about this subroutine? Yep, go ahead. Question? No? Okay. Now, of course, in C, you can always write the entire program on one line, or the entire subroutine on one line using ternary operators. So you can say unsigned n, and then just have one single return here. So the one single return is going to depend on whether n does equal to 0 or not. If it does, it is a 1. If not, it is 2 times P2 of n minus 1. So that's the other way to do it. Same kind of logic.
But we have to flatten it. But we have to flatten it, so it's going to be different.
We have to flatten it, correct. So if you want to,
explicit.
Right. So to flatten it, the second one is a little bit harder to flatten because you have to compute the value that you're returning first, and then you do the return. And I didn't talk about how to flatten a ternary operator. Yeah. All right, but the logic is the same. Okay. So now the question is, how do we do this in assembly code? Okay. So we start with P2 as a label, and then what do we do? What does the stack look like when you're at the entry point of P2? So we want to look at the stack pointer first, or look at the stack. What is on the stack? Okay, so the return address is the one that is pointed to by D, register D, which is our stack pointer. So this is going to be the return address. What else can we expect on the stack?
The value.
The parameter. Okay, very good. Okay, so the parameter is on the stack as well. But where is it?
The one below it, or whatever it is. That's the top of the stack. It's the one above.
It's above it, exactly. So it's 1 byte above where D points to. The parameter end is right here. So it's always a good idea, when you're writing the subroutine in assembly code, it's always a good idea to take a look at what the stack should have at that point.
So n is the top? Is n the top?
Yes.
Okay.
So n has a higher address compared to the return address.
Okay.
Because it is pushed first. Whatever you push first has a higher address. Okay, so then what do? We try to implement the code in C. Either way, we have to compare n against 0. So you can do it here, you can do it here, but you cannot avoid a comparison to 0. Okay, so, well, what do? Well, first of all, we have to get n back. So how do we get n back?
We have to store it.
Copy D to C.
Copy D first. Okay, very good. Because the first thing is we have to start with D. We have no idea where to find the parameter, except we know it is close to where D is pointing to. So what we can do first,
D is the top of the stack.
D is quote-unquote logically the top of the stack, but it's actually at the lowest point where you have put something on the stack. So the first thing is a CPR, CD. So what this instruction is doing is so that D points to the return address, but C is the same way. So C and D are both pointing to the return address. Now, you don't want to mess around with D because it's the stack pointer, but C is just some other register, so we are free to kind of make modifications to C without any problem. So now we can say increase C. After that, C is no longer pointing to the return address, but it is now pointing to N. The other way to denote this is C is now the address of N. Is that part okay? So I'm trying to use C notation to relate what we're doing right now with something that you learned in cisp310. That's great. C has the location already. So if I do a LD at this point, okay, I can put it into register A, register B, it doesn't really matter which one. If I put it into register A, whatever C is pointing to, so now C is actually the value of N. It used to be the address of N, it is now the actual value of N. Other, oh, A has, yep, correct. Thank you. So register A now has the value of parameter N, which means we're ready for compare. So we can use an LDI instruction or a sub instruction, either way works okay. So we can use a sub instruction to turn one of the registers, except for D and A in this case, into 0. So we can subtract, okay, B, B, C is fine, okay, we can reuse C. So C is now 0. Then we can do a compare. So when we compare, because this is using the unsigned representation, equal to 0 versus not equal to 0 is sufficient to tell us what to do. So we just compare A to B, C in this case. Okay, so we are comparing A, some kind of relationship with 0. A is N, so we are basically saying, okay, let's compare N to 0. We only got JZI, we don't have a JNZ or not 0 to. So JNZ to some place where we can return a 1, right? So we say return 1, which is a label defined down here. This is my usual way of commenting. If I have a conditional branch, I will also write down some comments of what it means to continue execution. So to continue execution, it means N does not equal to 0, which means we have to call recursively. Are we still doing okay at this point with this program? But because this is the else case, it also means that if I don't want to return in the middle of a branch, I need to do an unconditional branch to the end of P2. And I'm going to define the end of P2 down here, just like that. All right. So now we can backfill this code here. When N does not equal to 0, this is what we want to do. In both cases, this is what we want to do. We want to put the result of 2 times P2 of N minus 1 into register A. Which also means the first thing we need to do is to call P2 recursively, but do not use N itself as the parameter. We want to use N minus 1 as the parameter. So we decrement A first, because A already has the value of N. So at this point, A equals to N minus 1. And we are changing a register. We are not changing the parameter that is living on the stack. So the parameter which is really living on the stack is not changed at this point. Then we have to push it on the stack. To push something on the stack, we decrement the stack pointer. Okay. Allocate byte for parameter N. Then we do an ST instruction, store to the new location that the stack pointer is pointing to with the value of A. So this is just pushing N minus 1 on stack. Then we are ready to call the subroutine. To call the subroutine, we have to reserve another byte on stack, use an LDI instruction to initialize one of the variables with the return continuation address. So this time we'll just say, P2 continuation address 1, which is going to be defined here. And then we store that onto the stack. Push return address on stack. So are there any questions about this code up to this point? And don't forget the actual jump instruction. This is where it looks kind of weird, because it looks like we have a loop, right? Because we started this execution at label P2, and we are now continuing execution label P2. Does look like a loop. This is actually how some programming languages implement loops. Is they don't have iterations like while loops, but they can do recursion. And recursion can have the same effect as normal loops. So we're still doing okay so far with this. So when you look at this entire thing, this is representing the recursive call. This block of code is really doing this part of the C code. Is that okay? So when we return, what do we have? Well, upon return, register A is going to have P2 of n-1 at this point. And my job is to double that. To double that is fairly easy. We have to add A to A itself. That's doubling the value of A, which also puts the value into register A, which is where we want it. So this is great. So by the time we get to P2, we can just continue execution. This label is representing the fact that we want to store a 1 into register A. Okay, so LDI A1 will do it. We can also kind of do it in a different way. If you want to save 1 byte of instruction, you can also do increment A. Because the only reason why we are here is because of the JZI instruction. But the only reason why the JZI would branch is because A does equal to C, but C is already a 0, which guarantees that A is a 0, which means increment A will make A equal to 1. Okay, so increment A will do the job. LDI A1 would also do the same job. We get the same thing done. By the time we get to the end, it's time to return. Oh, I forgot one thing. One thing. It's kind of important. Okay, let me continue to forget that, and then we'll see what happens. Okay. So at this point, we're going to say, okay, the return address should be pointed to by the stack pointer. So we're going to load register B because we don't want to mess up A with whatever D is pointing to. Okay, so we retrieve return address from stack. We increment D to free the byte, to free the return address. And then we do a JMP instruction to B to continue execution in caller. That should be the end of the entire thing. But I forgot one thing. What do you think I forgot? Yep.
Forgot to deallocate the parameters.
Yep. The one single parameter. Yep.
Doing this every time.
So if I don't deallocate the parameter, seems like the only problem is I'll be consuming more stack space than I really should. But that's not the effect, right?
Memory leak?
It's not a memory leak. This one has a more immediate symptom.
Oh no.
Okay, so the problem is, so let me point out what the problem is, and then we'll all kind of think about the actual effect of this problem. The problem is when I continue execution over here, I have no use of the parameter that I pushed on the stack earlier. In other words, this parameter that we push on the stack is no longer useful to me anymore. But the stack still has it. In other words, the stack pointer is pointing to n-1 at this point. It's still on the stack pointer is pointing to it. Is that okay? And I continue with this code without deallocating. In other words, I compute the correct answer. I go all the way to the end of the subroutine, and then I do the return code. What do you think this B is going to be when I say, okay, whatever the stack point is pointing to, put it into B? What do you think B is going to be? It's not the return address anymore, is it? It is n-1. In other words, for getting to shrink the stack to free up the parameters, it's not just quote unquote wasting space on the stack. It is also messing up the assumption that the stack pointer is pointing to the return address at the very end of a subroutine. But what is the behavior of this program? If I continue to miss that one single instruction, what would be the symptom of this program? I'm not sure whether it will loop forever, but it will go to the wrong address. it's going to use n minus 1 as the actual return point. So now it all depends on what is n minus 1. If n minus 1 is an actual location where I can execute instruction, it will go there to execute instruction, which is erroneous.
And you're going to start opening up Windows Explorer when you're trying to use Firefox.
Well, it's not going to do that, but it will go to the wrong location. Okay. All right. So somebody is going to make that mistake at some point, because I have made this mistake many, many times. So the question is, assuming that you are going to make this mistake sooner or later, how do you debug your program? How do you say, okay, my program has crashed, it doesn't work the way it's supposed to, but how do you identify this is the problem?
Step through it.
You can step through it, but you can also use a trace. In other words, what you do is you use a trace, you track down PC, and you say, am I returning back to the caller's place at the right time? That is what you do. So we're going to put this instruction here, but have it commented out. So we'll say that we really need this instruction here to deallocate parameter from the stack, but I will keep it commented out. In other words, I know what I'm supposed to do, but I want to look at the behavior of this program when it's erroneous, and then we want to figure out, okay, how do we debug this? How do we find this out? All right, so this subroutine is all done. When the subroutine is done, we'll finish the entire program. This part is not really necessary. Okay, so we have initialized the stack pointer. And then this part is also not needed, but it makes it clear where the main subroutine is located. And this one will stop the entire program, but I have a suspicion that we may not get back to here, or we get back to here not at the right time. Okay?
It'd be hilarious if it just jumped straight to halt though.
Huh?
It'd be hilarious if it's
It might. It depends on what n is, right?
Yeah.
Okay, so we're going to call the subroutine, and we say, let's use, let's see, let's compute 8. Okay. In other words, we will put a 3 into A, and then we say decrement D, stda. So we push 3 as parameter n, right? And then we call the subroutine. Now we call the subroutine. And to call the subroutine, we are going to LDIA with main continuation address 1, which is here. And then after that, we say decrement D, and then stda, push return address on stack. And then we now continue execution at P2. And this one, with this one, I do remember when it doesn't really count, I remember to deallocate that return out parameter from the stack. Deallocate from n from stack. Okay.
Your main continue label is missing 1.
Oh, okay. The assembler should catch that one.
It would have caught it.
Yeah. Okay, so that's my entire program. It still has that one bug for sure. Okay, whether we have some additional bugs or not, I'm not 100% sure. So we copy this entire thing, and we need to fire up the assembler. Has anyone tried to use the assembler offline? Not yet? Okay.
Or downloading the file.
Yeah, there's a way to do it offline, but you have to use Chrome. You have to install an extension of Chrome first. So I think that basically loads in the code of the spreadsheet engine itself. Then you can actually use the spreadsheet supposedly when you're offline. So that might come in handy. I haven't tried it myself. Okay, I need to do that. To processor, shared processor, and the assembler. Just paste. The program has some extra stuff here. There's no need to really get rid of the other stuff that's on this in this program, because That's after a unconditional branch, so there's no way the program will continue execution where it's not supposed to. But we'll just kind of get rid of those too. We go to RAM file. There are no mistakes. We'll download the program, or the compiled program. We call it P2. Now we can start up the simulator. Control R to reset the entire thing, and then we will load p2.csv as our program. Now remember, we have this bug, and we want to find out, how do we debug this program? So we go to simulate, we turn on logging. The minimum that you should turn on, when you're debugging your program is PC. There's no way you can avoid the PC. You can also go to the register bank and at least have register D, which is the stack pointer. So those two, are kind of really, really important. And since we know that we are going to store something on the stack, it also means, it might be useful to keep track of what is on the stack. So you look at RAM, and just put the last few locations into the log. So if you're not really sure, you can just put a whole bunch. Okay. So I'm just putting a whole bunch of stuff, onto the trays. We are not going to use beyond the last two locations. In other words, location 255 should have the return address. I take it back because it's recursive. So 255 has a return address parameter. Excuse me. 255 has a parameter. 254 has a return address, and then 253 we have the second invocation. 252, 251 we have the third invocation. So I think we'll get up to maybe 248, 249, because it won't stop until n equals to 0. So when you count 3, 2, 1, 0, so there are 4 invocations. Each invocation uses up 2 bytes, so we will consume actually 8 bytes on the stack. All right, so let's do that. So we'll take out the, we'll put 8 bytes. We'll put 10 bytes into the trace. Get rid of these, and there are 8. Now we have 10. Okay, there we go. So we are adding the last 10 locations on the stack to the trace. Are there any questions about how I set up the trace? Questions? You all good? Okay. I want to point out there are a few things you can change in terms of how you set up the project, just to make it more convenient. So when you go to preferences, you can go to, let's see here, experimental, layout. Okay, so when you go to layout, when you poke a wire, you can display things in octal, binary, signed, decimal. So in this class, I think hexadecimal may be the most convenient. But this doesn't apply to the trace. It's just when you look at things from a layout perspective. The second radix is the other one because it would display in a slash. So I think with the second one we can use unsigned decimal if that's useful. Window experiment. Okay, so that's not helpful. There's nothing to help us with the logging. It's still going to log in binary, unfortunately. We can take a look at one more time and see if there are options to change here. Okay. Nope, these are the same entries that we have seen already. Oh, wait, there's a project option. Simulation, toolbar. I don't think these are going to be helpful. Okay. Okay, so unfortunately there may not be a way to turn the format of the trace from binary to hexadecimal, which is going to be a lot more handy. All right, so shall we go? Okay, so we'll do a Control-C, Control-K, and you can see the program is going all over the place. It doesn't stop. Okay, looks like it's in some kind of a loop, right? So we go to Simulate, we go to Logging, and this time we go to the table, and we try to find out what is going on with this program. It's going to be a little bit difficult because it is a little bit wide, and there's no way to export it once it is in the table. All right, so if this is not helpful, what we do is we turn on the file option. Okay, so we go here and then we select a file, p2.log. And then we basically reset the whole thing. So Control R to reset the entire thing, reload the image. Let's see, reset simulation. Uh-oh. Ooh, look at that. Okay, so I think Logisim itself has crashed. Time to close it. And start it over again. Okay. All right, we'll do it one more time. Go to the registers, keep track of register D, and then we go to RAM locations. Keep track of the last 10 locations, 255 up down to 246. And then we go to file, because this time we want to enable the use of a file, p2.log. Okay. And load the program in. And then we can run it. There we go. All right, Control K, stop the trace. And then we go to a command line to kind of take a look at what is in that file. Right. Doesn't show very well, does it? Okay, they are using tabs to separate these things. So they're using tabs to separate the values, which also means there is a way to look at this from a spreadsheet's perspective. So I'm going to use a new spreadsheet for this purpose, and you can do the same thing. Just open a new spreadsheet, and I think there's a way to import a file. Let me see. There we go. Import. Upload, and then we go to the temp folder, p2.log. Okay. Supported types. Okay. Okay. So let's rename the file first. So what Google Sheets was complaining is it doesn't know what to do with this file because it's not using TSV as an extension. So mvp2.tsv is just changing the name of p2.log to p2.tsv, which stands for tab separated value. So now we should be able to import it. So once again, import. We want to upload a file from here. Open. And we want to replace the sheet. Okay. Separator is a tab. And we click import. Yep, we got it. It looks really ugly because everything is in binary. All right, so this is basically the program is not working. So you have to find out where does it give you the sign that it is not working. You look at the program counter, okay? It keeps incrementing. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, this is 11, and then we move on to 14. So from here to here, there's a call. Okay, this is a call. So we want to label this one here and say, are we using anything on the stack? You can see that the stack pointer was originally 0. Now it is 255, and by the time we get here, it is 254, which makes sense because we have the parameter at location 255, and then we have the return address to main in 254. But it is always a good idea to double check. So we go all the way to the end of the RAM content, and then we say, okay, what are we seeing at the last few locations? This is our parameter. Label L is the parameter, which is n, which is 3. 1, 1 is 3, so that's good. This is supposed to be the return address. So the return address is supposed to be location C or 12 in memory. We go back to the assembler, go to the Assemble tab, and then you look at the return label from main. It does have an address of 12, which is 0C or 00001100 in binary. So far so good. The program is working fine at this point. And then we continue with this program. Okay, so it continues execution. This is inside the subroutine. This is location 14, 15, 16, 17, 18, 19, and then we got 20, 21, 22, 23, 23, 24, 24, 25, 25, 26, 29, 30, 30, 30, 31, and then we get back to the beginning. In other words, this is telling us that this is the recursive call. Is that okay? So the recursive call is getting back to location 14. We double check here and ask, is the label P2 at location 14? And right here it says it is location 14. So far so good. The recursive call itself was successful. Now if that recursive call is successful, did we put the right thing on the stack? So we go back here, and then we slide all the way to the end of the trace and say, okay, what is on the stack right now? We have the second parameter and the return address, again. But this return address is not returning to main. This is the return address to go back to P2 after the call. It has a value of 1 plus 14, or 16 plus 14, which is location 30. We double check that. We go back to here, and then we look at the continuation point on line 31 of the program, and it is in fact at location 30. Okay, so the recursive call itself was successful. The first recursive call anyway. And then we keep tracking it. Okay. So we want to look at the next time we have 1110 in column A. So keep going, keep going, keep going. And now this is another recursive call. And every time we have a recursive call, we look at the stack content. So this time the stack content has 1 with a return address here. Okay, so that's good. Wait, I think did I miss one of the recursive calls? Yep, I did. Sorry, I missed this recursive call here. So this is the recursive call where 1 is the parameter on the stack. This is the return address back to P2. So far so good. Things are still looking good. And this is the last one. This is our recursive call, or supposed to be the last recursive call to the subroutine. And when we look at the stack, we can see that we have a parameter of 0, and then we have the return address on the stack as well. So far everything is good. So this goes through some computation. Okay, this is location 14, 15, 16, 17, 18, 19, 20. And then we jump to this location here. So right here, we have a branch to some location that we have not used before. So we look at this location. This is location 20, because this 10001 means we have 116. 0100 means we have a 4. 16 plus 4 is 20. So at location 20, or maybe one location before that, we have a branch instruction that somehow ended up here at 10000001. In other words, we want to look at this transition of the program counter. So we're looking at location 19-ish in the code. So we look this up. Location 19 is this instruction, is a conditional branch, and the conditional branch is going to return 1 because this time a does equal to 0, and return 1 is all the way down here with an address of 33. Whoops. And is this 33? The 0010 is a 2, which means we have 2 16s, and then plus the 1, we indeed have 33. So the conditional branch works fine too. Cool. So at the conditional branch, we have 31, 32, 33, 34. No, this is 30, 33, 34, 35, 36, 36, 37, and then this is supposed to be a return because it changed. Okay, so first of all, we look up this location. We look up the location of 2 times 16 plus 4, because this is the location that we are actually doing the branch. So we are supposed to go back to location 36. So 2 times 32 plus 4 is 36. So we look at location 36. Okay, this is the unconditional branch that supposedly will bring us back to the caller. And the continuation point should be P2 underscore cont 1. So the question is, are we continuing over there? The answer is, yep, we are. Okay, because this location is location 30, which is 16 plus 14, which is a 1E. Okay. And then when we look at the trace, this is indeed 1E. 0001 is 1, 1110 is E. So we return from the last invocation to the second last invocation correctly. Really? We had that bug. How come the bug is not causing problem here? Because we didn't get to the recursion code. The last invocation did not push the parameter. Is that okay?
Wait, what? So what happened?
Okay, so we're at the very last invocation. The very last invocation returned correctly. But that's because the very last invocation did not call itself. If it did not call itself, it didn't push any parameters, and therefore there's no way of forgetting to pop the parameter from the stack. So the stack is actually okay because it skipped over the entire part of calling itself, which is the problematic code.
Okay.
Okay? But now that we are back to the second last invocation, we'll have a problem. So back to the second last invocation. So we are back to, okay. So in terms of the code, we are now here. And it will do the add AA, and then we'll go to the end, and then we'll attempt to return. But this time it will have a problem. So we continue execution. This is location 30, 31. And this is 32, 34. And then this is 30. 35, 36, 36, 37, and then back to 0. So we definitely have an issue with these two instructions. Because we are not supposed to go back to location 0. That's for sure. So when this happens, we want to look up the location corresponding to the 2.5 or the 2.4, because it's usually 1 byte past the actual instruction. So we want to look at location in hexadecimal 2.4, which is 36 in decimal. Okay. So we look up location 36 and ask, okay, what is that? Location 36 has an unconditional branch instruction. Cool, okay? We are supposed to get there to return to the caller. But how come when we return to location 0? That's because the stack pointer is messed up. How do we know the stack pointer is messed up? Column B is our stack pointer, right? The stack pointer is supposed to point to the return address when we are at the end of the execution of a subroutine. Okay? So when we look at the code, we are basically saying when we execute this line, which is at location 34, the stack pointer should point to the return address. Is that okay? That's the assumption. So we look at this location. 34 in decimal is 22 in hexadecimal, which is 00100010 in binary. So we are basically looking at this portion here and say, at this time, the stack pointer should point to the return address. This is our stack pointer right here. It's 11111001, which is 200 and is 255 minus 6. So this is location 249. Does that make any sense? Okay. So we want to look at location 249. And this is where I kind of need to pull a trick of using spreadsheets. There's a little bar here. If you scroll this bar down, you can kind of keep the scrolling separate so that we can scroll the bottom part without scrolling the top part. Okay. So now we can go to, okay, I can't see these numbers, unfortunately. We can always pop it here, but then we lose, this is 249, but you can see the entire column of 249 are all zeros. No wonder it went to continue execution at location 0. Is that making any sense? But why is the stack pointer pointing to the wrong location? What is this? It is the parameter. This is a parameter, right? And this is a parameter to the very last invocation where n equals to 0. I left it on the stack. I should have deallocated this so that the stack pointer really should be pointing to this location instead. It should be pointing to location 250, which actually does contain the correct return address back to P2. Is that okay so far? Sort of? It's kind of important because this is how we debug a program.
So what I'm getting is just don't have any bugs. So the solution is just don't have any bugs.
That's not possible. When you do have bugs, you just have to kind of trace the program. But there are important things that you have to trace first. The program counter, register D, and the last few locations on the stack. Those are basically the crucial stuff that you have to track when you're trying to debug a program. Okay, so that's how we found the problem. The problem is the stack pointer is pointing here instead of here, which means we forgot to increment the stack pointer. Okay, so we go back to the, oops, where's my editor? Okay, let me close all the ones that I don't use. Where did I put it? Oh, okay. So when we look at the code, which I think is in a notepad here, this is the missing instruction. If I remove the comment and include the increment, then it will do it correctly. Well, let's try that. So we can now go back to the spreadsheet over here. And because this time I'm just uncommenting a line that is already in the source, I can just do it here. In other words, I go to this line, go to line 32, and just say, okay, now we're putting that particular instruction back. And the program is reassembled. Go to the RAM file, re-download this. Just overwrite the other file. Go back to Logisim, Control R. I think this is not working, so we'll close the entire thing and restart Logisim. And it looks like it has the same problem as last time, exactly the same problem. And it seemed to have something to do with RAM logger is causing the problem. So that part crashed the program. The developer is no longer actively debugging the program, debugging this code. But remember, when you download and install Logisim, you get the entire source code. So I can potentially go through this and actually find out where the problem is and fix it. Not in class though.
What's it written in? Do you know what it's written in?
Java.
Oh, right, Java, yeah.
Yep. Which is great because now it runs on every platform. Yep. All right. So we'll track the same way, which is what is causing the problem. So it will crash this time too. I mean, Logic sim itself is going to crash, but the program is going to be okay. Or we can not do any logging, and just say that this program is going to work, so that A should have a value of, we pass a 3 to P2, should be 8, exactly, because it's 2 to the power of 3, which is supposed to be 8. So we look at register bank, and it does have a value of 8, so we got it done. And we should be back to the location, the halt instruction. So when we look at the source code, or when we look at the assembles window, the halt instruction is right here. It is at location 13, which means the program counter should be 14, which is 0001 0100. So we switch back to the simulator, and we double check. Huh?
What is the program counter displayed?
Oh, right. The program counter is 14, which is correct. I shouldn't say 14, should have said 14 because it's base 10 14. And 0E is 14 because F is 50. Yeah. All right. So are there any questions about this session? Because I intentionally put a bug into the program, and then knowing that there's a problem with the program, we go through the trace and we found that the problem does not show up with the last invocation because the last invocation skipped the portion that does the call, which is the problem. It is the second last invocation that showed up the problem. Yep.
Last class period, you put your assembly code into I think it was a spreadsheet, and you tracked it.
Mm-hmm.
Did you make that public? Where'd you put it?
The last one? I do not remember.
It was not that, but it was you know what I'm talking about? You put the code into a spreadsheet, and then you tracked RAM and the contents of registers A, B, and C, and D in a spreadsheet.
Okay.
To help express what's happening in the program.
I think, okay, let me check that. Because if I did do that, it's going to be, I probably send it to you by an announcement. I could be wrong. Did I do it in Google Sheet? Probably so, because I haven't used
I mean, it was a spreadsheet, so that'd be Google Sheet.
Yeah, if it's Google Sheet, it will still be there. But I'm thinking that I might have. Nope, not here. I can always go to my drive.
The most recent.
Yep. From last week. Earlier this week.
So it
It'll
Wednesday.
be probably this one. Nope. Was it Wednesday or was it Monday?
It was Wednesday, it's 25th.
Nope. We looked at this one already, so it's not here. Pretty sure I did not delete the file either. So
Is the timestamp last opened or last edited?
it's last. That's a good question. Take a look at this one. Nope, that's just our trace that we did today.
It's the most recent.
It's last recently opened. I have a feeling it's on Monday.
I think it's
Yep.
you passed it already. I think it's the one about birthdays. Because the one you opened, it went to the top.
Okay, you mean this one?
Yeah.
Take a look.
Yeah.
Yep. Oh, yay! We found it.
Like,
Okay. Let me put it and rename it. Okay.
doing something like this with a program that had a bug would be a good idea.
But that's going to be long. This
Good.
one is going to be really long.
That's true. Maybe
But
not.
you can probably do it yourself because the trace is actually here. We actually had this trace, except we don't have the line number. We just have the program counter. That's all we had.
Yeah.
Yep. So when you look at the stuff that we did today, which is this one, one thing, if you're working on something like this, what I would do is to turn these labels back to, something that's easier to read. This is the stack pointer, basically, and this is location 246. So just use a more concise representation. So this way, it's easier for you to look at the actual content. But that's the trace. I mean, that basically is what we have. The only difference is this one only uses the program counter instead of line number. So when you look at the program counter, you have to go back to the assembler, go to the assemble window itself, and track down these numbers. This is the address. This is in let's see. No, take it back. These are the addresses. This is in decimal. This is in hexadecimal. So it's a little bit more, troublesome because you have to kind of look up the address and then find out what line it is corresponding to. But they're all here. If you make your own spreadsheet, when you make your own copy, this is one thing that you might want to consider doing. So I'm giving the suggestion to the entire class, and in fact, I will do it here too. So I would add a new tab for debugging purposes. I'll add a new tab. So in this new tab, I'm going to move it all the way to maybe right next to source, or maybe we can just reuse source. This is for error reporting. We'll just do it separately. Okay. So with this one, the first cell is just really the source code. So I'm going to put it. Oops. I have to put it at the right place first. So this one is source because I'm editing that particular cell, it is over. We just have to type it. There we go. Okay, so the column A is the source code, and then we just have to find a way to look at the address. So the address, you can get it from assemble. Let's see, we want it in binary, don't we? Because the trace itself is in binary, so we want to represent the address in binary. So in this case, we want to say decimal to binary, and it's going to be going to the assemble window, and it's going to be column V, this one. And we want to make sure that we are using 8 bits so that this matches what you see in the trace. And then we take these two and we just make it 300 rows long to match the maximum size of the program. Here we go. Now you have an address corresponding to each line of the source code, which makes reading the trace easier, because now when you look at column B, that corresponds to 1 plus, column B corresponds to PC minus 1 in the trace, because when you look at the PC, by the time it has effect, it is already 1 past the actual address of the opcode. So this makes debugging a little bit easier. And since I made this change to the source document, when you make a copy of this file again, it would incorporate this. And I would name, instead of using sheet 9, we'll just call it debug source debug. So this way you have an easy way to map an address back to the line of source code, so it's easier to read. Is that okay? Cool. Because the next thing we'll do is to allow you to copy and paste the trace from Logisim, and it will automatically figure out what line of code is executed, all the other stuff.
We?
Hmm?
You said we?
I said we, yes. It's a lookup function. There's a lookup function, but you have to massage the number a little bit because the trace uses a slightly different way of representing the zeros and ones. So you have to kind of take out that space between the blocks of binary digits. Then you do a bin to DEC conversion, and then do a match. That would make it work.
So if you wanted to right now, if you wanted to turn all these into hex, you wouldn't be able to because of the space.
Correct. But there are string functions to take care of that space. Yep.
Yeah. Replace.
Yep. You can do a regular expression replaced in Google Sheets, which is missing from most other spreadsheet programs. But Google Sheets has a regular expression and capabilities. Yep. So that would be kind of a cool little project. So we doing okay so far with this stuff? So I'm just kind of extending the tool itself a little bit, to make it easier for you guys to debug your program. So are you guys done with the homework due on Wednesday, or you guys still working on it? Some of you are still working? Is anyone done with that program? Okay. Very good. All right, so has anyone not started on that one yet? Well, okay, if you haven't started, the discussion today may be helpful because it allows you to visualize the execution of a program so you can actually see what is on the stack at any time. So that might be useful. All right. Any questions? So on Wednesday, okay, so now we have a problem because originally I said you guys would have the practice exam on Wednesday, but because I had to postpone the exam of cisp 440 right before this class, so I'm going to postpone the test of this class as well by another class, so you won't have the second exam until the Monday following next Monday.
13th.
Yep. Is that okay?
So not this coming week, but the next one.
2 weeks.
Correct.
Yeah.
In 2 weeks.
Yeah, because we practiced the exam on Monday.
Because I don't want the 440 exam to fall on the same day as
you.
310. But I can only do it for the exams. So for the final exam, I cannot make that modification. I have to follow the college exam schedule.
Yep. Bite the bullet on that one.
You just have to bring in more caffeine.
More caffeine.
More caffeine, yes. All right, so I'm going to end today's lecture. If you are working on your homework assignment, you can do it in the lab. I can take a look at your program. And I'm going to stop this whole lecture here.